Welcome to Lecture Online, and here we're going to find the electric field at some point at a certain distance away from an infinite line of charge. Now, of course, there's no such thing in the world as an infinite line of charge. The universe isn't big enough for that. But the reason why we want to do it like this is because even if it's not infinite, and of course it's not going to be in the real world, if the position of the point that we're interested in finding the electric field of at that location, if that's close enough to a long line of charge, the result that we get here is pretty well close to what it would be if we assume that it's infinitely long. Later on, we'll do an example where the line will not be infinitely long, where there'll be a finite distance that's relatively small compared to the distance to the point of interest. But if the point of interest is fairly close to the line of charge, we can just assume it's an infinite line of charge, and we're going to go ahead and figure out the result of that. Now, the charge on this line here, we can say that it has a certain, what we call linear charge density, charge per unit length in terms of coulombs per meter. So a certain number of coulombs, probably not coulombs, they're probably microcoulombs or something like that, but a certain amount of charge per unit length. We're distance a away from it and want to know what the electric field is at that location. So how do we do that? Well, the first thing we're going to do is find a small little segment right here. Here's a small little segment. And the amount of charge residing in that little segment is going to be a small amount of dq. So a small amount of charge, we call that a dq. And how do we find the relationship between dq and the length of this charge? Well, we know that the length of this charge, if we assume that the distance from there to there, if we assume the distance here is equal to x, and x is a variable because I can move this little section anywhere I like, so that distance is x, then we know that the length of that small little segment right here is dx. And that dx will contain a certain amount of charge dq. So how do we find the relationship between those two? Well, it turns out if this is the linear charge density, if we take the linear charge density and multiply times the length, we get the amount of charge on there. So we can write that dq, therefore, is equal to the linear charge density times dx. All right, so far so good. Now let's draw a line from that little segment to the point of interest. And we can say that that distance from there to there, let's call that r. And of course, r is going to be related to x and a using Pythagorean theorem. We'll get there in just a moment. So now we can say that the amount of electric field we experience at this location due to this small little segment right there is going to be a small amount of dE. And of course, what we want to do right now is just find the magnitude of that. And using the general equation for the electric field, we can therefore say that dE, the magnitude of dE, is equal to k, times the charge that causes it, which is dq, divided by the distance from that location to the charge that causes it squared, so divided by r squared. All right, now dq, of course, is equal to the linear charge density times dx, and instead of r, we can write what r is equal to, so this can be written as k times the linear charge density times dx divided by, and of course, that's going to be x squared plus a squared. Now, r is the square root of x squared plus a squared, but since r is squared, we have to square the square root, so that negates it. We get x squared plus a squared. So that is the magnitude of this of the electric field at that location due to this small charge. Now remember, there's actually a much easier way to do this problem. We can use Gauss's law, and I believe I do have a video out there where you can actually find the electric field at this location using Gauss's law. A lot easier. But some of the viewers said, well, we're also supposed to figure out how to do this in this particular fashion. That's why we added this video as well. All right. Now notice that this vector quantity right here will have a horizontal component and will have a vertical component. So this would be the dE in the x direction, and this would be the dE in the y direction. And for every little line segment, as I go and move the little line segment over, you can see that for every one of those, you'll have a horizontal component and a vertical component. But then also you will have line segments on the other side. So when you start building the line segments over here, and then finding the electric field due to that line charge, notice that those will also have vertical and horizontal components. So that would be the dE due to this little component right there. And you can see then that that will also have a horizontal and a vertical component. And notice that since there's the same number of segments below this point as there will be above the point, the vertical components will cancel out, and the only components remaining will be the horizontal components. So the only thing what we have to do here is simply add up all the horizontal components. Of course, by now you've probably figured out that, I got the wrong cap on here. But now you've figured out that what we're going to do here is we're simply going to do some sort of integration by summing up all these small little infinitesimal small little segments with small little dq's on them. So now what we need to do is find out how big the DEX component is relative to the DE. And of course, what we can say here is that we have an angle right here, which is theta, which is the same angle as this angle right here, theta. So you can see that these two are equal angles. And so to find the DEX component, we can say that the DEX is equal to the DE times the cosine of that angle, because it's adjacent side. So that means that this is equal to k times lambda times dx divided by x squared plus a squared times the cosine of theta. Now, what is the cosine of theta in terms of these things right here? Well, notice if I keep drawing this line this way and keep drawing this line this way, this here is the opposite side to this angle. Here, this is the adjacent side to the angle, and there's the hypotenuse. Now, the hypotenuse distance is r. This adjacent side here is a, and the opposite side there is x. Now, since we're dealing with the cosine of theta, remember that the definition of the cosine of theta is equal to the adjacent side divided by the hypotenuse. And in this particular case, the adjacent side is a, and the hypotenuse is r. And of course, r can be written as the square root of a squared plus x squared. So we can replace the cosine of theta by this quantity right there in our equation. And so instead of writing the cosine of theta, we're going to write this as a divided by the square root of x squared plus a squared. Now combining that, we can say that this is therefore equal to k times lambda. Lambda is called the linear charge density times a times dx divided by x squared plus a squared to the 3/2 power. All right, so now we have the x component of the electric field of an arbitrary line segment. Now, of course, to find the total E sub x, we're simply going to add all these up. And so to find that, we say the total E sub x is equal to the sum of all the little components that you get from each of the segments right there. And so that would be equal to the integral of this. So the integral of k times lambda times a times dx divided by x squared plus a squared to the 3/2 power. Now, of course, if we're integrating that, we have to go all the way from this location all the way to positive infinity in the x direction, and from this location all the way into the negative infinity to negative infinity in the negative x direction. So we're going to go from minus infinity all the way to positive infinity. All right, now realizing that a is simply a fixed distance, so that's a constant, k is a constant, lambda is a constant, so that means that we can write this as E sub x is equal, we'll pull the constants out of the integral sign, so we have k lambda a times the integral from minus infinity to plus infinity of what we have remaining, which is dx, divided by x squared plus a squared to the 3/2 power. Now, we have to integrate that. I say, wow, if you have never seen the integral before, you're probably not going to know how to do that. But if you go to one of the integral tables, you'll find that it's not that hard because, and also that you're going to see this quite often using this in this kind of phenomenon. So we find the electric field, Coulomb's law and all that. This particular integral appears a lot. And turns out the integral then turns out to be, so when we multiply this times, we get that, so we get x divided by a squared times x squared plus a squared to the 1/2 power. So that's the integral, that's the result of this particular integral. So you get an x, the variable x in the numerator, you get this to the 1/2 power, and we have an a squared out here. We're going to then evaluate that from minus infinity all the way to positive infinity. Right, so the a squared is a constant that can come out, and that will then of course cancel out with this one right here. So this cancels out with that. And then the a comes in the denominator, so this is equal to k lambda divided by a times. When we plug in the upper limit, we get infinity divided by infinity square plus a squared to the 1/2 power. Minus, when we plug in the lower limit, which is minus infinity divided by minus infinity squared plus a squared all to the 1/2 power. Like that. Now, infinity squared plus a squared, well, the a squared is so small relative to infinity, we might as well just ignore it, like it's not there. Same on this side, we can just ignore that. And then we see that infinity squared to the 1/2 power is simply infinity, and infinity divided by infinity is 1. So this can be written as k lambda divided by a times 1. Now the minus times this minus makes that a plus, and here we get the exact same result as we had there, so we get plus 1. And so finally in the end, this therefore is equal to, so the E field, the magnitude of the E field in the x direction is equal to 2k lambda divided by a. That's the magnitude of that, and that would be the total, that would of course be the total electric field at this location. Since it's to the right, we can write it as a vector form. We can say that E is therefore equal to 2k lambda divided by a in the positive x direction. So that would, in this particular case, look like that. So the answer is fairly straightforward. It's simply twice the constant k times the linear charge density divided by the distance away from that line. And that's how you find the electric field of an infinite line of charge.